Welcome to Programming for Problem Solving. We'll start with an introduction to computers in Unit 1, then systematically build your C programming skills. We encourage you to ask questions, collaborate, and seek help. Programming can be challenging sometimes, but it's an incredibly rewarding journey. Topics covered in Unit 1. Introduction to components of a computer system. Idea of algorithm with flowcharts and pseudocodes. From algorithms to programs. History of computing, computer generations. Sample questions. A computer is an electronic device that processes, stores and manages data. Its basic components are hardware and software. For a computer user, the software provides the instructions and the hardware executes the instructions following input process output, IPO, cycle. Check the diagram carefully. Here, input data is processed by program instructions which generates information as output. For example, input data for a rectangle can be length 5 and width 10, and the program for calculating that rectangle area will produce information output 50. This is also a cycle as the output from one process can become the input for another process. Let's review the basic components of computer hardware. Modern computer hardware is based on the von Neumann architecture, prepared in 1945, though significantly evolved. You may pause the video and check the diagram carefully. 1. Accept data, input device examples, keyboard, mouse, scanner, microphone, touchscreen, camera, sensors, etc. 2. Store data and program in main memory, meaning RAM, for execution and secondary memory, meaning disk, for long-term storage. 3. Process data, using ALU, arithmetic logic unit. 4. Display results, output, monitor, printer, speakers. 5. Control and coordinate above operations inside a computer, using CU, control unit. Hardware components. Processor, CPU, is the brain of the computer. Processes data and runs program in binary form, which is represented as bits, zeros and ones. Components. 1. Arithmetic logic unit ALU performs mathematical and logical operations. 2. Control unit CU manages instruction execution. Examples, Intel Core i7, AMD Ryzen, etc. Computer memory has following 4 components. 1. Random access memory, RAM, also known as primary memory. Program and data must be loaded from disk to the main memory or RAM for execution as the CPU cannot access these from the disk. Volatile memory, meaning data will be lost when power is off. Or provides faster access than disks. Examples, 8 GB DDR4, 16 GB DDR5, etc. 2. Read-only memory, ROM. Non-volatile memory, so it retains data without power. Stores essential system firmware or basic input-output system, BIOS, used for hardware initialization and bootstrapping, which means loading the operating system after the machine is turned on. 3. Registers, tiny and fast storage locations within the CPU for active data. 4. Cache memory, small, fast memory between CPU and RAM for frequently used data in modern computers, not supported in von Neumann architecture. Secondary memory, disk. Types, hard disk drive, HDD, solid-state drive, SSD, USB flash drive, memory card. Non-volatile, retains data without power. Stores operating system, applications, and user files. Besides hardware, the other important component inside a computer system is software. Software is a set of instructions, programs, that tell computer hardware what to do. Categorized as either application software or system software. Application software, programs designed for specific user tasks. Types. Word processors like MS Word. Spreadsheet like MS Excel. Web browsers like MS Edge, Mozilla Firefox, Google Chrome, etc. System software, programs that manage computer operations and provide services for application software. Types. Operating systems, OS Windows, Linux, Mac OS, etc. Language processors, compilers, interpreters, assemblers, device drivers, graphics driver, printer driver, network driver, utility programs, disk cleaners, antivirus software, firmware, BIOS/UEFI, embedded firmware for routers, firmware for IoT devices, etc. Program storage and execution. A program is written using a programming language, like C, Python, Java, C++, JavaScript, etc. It is compiled to create executable. Both source and executable are stored in secondary storage like disk. Executable must be loaded in main memory or RAM for execution by CPU. OS and language processors. Operating system, OS, is a software that manages hardware resources and provides common services for applications. It acts as an interface between computer users and hardware. Typical functions are memory management, process management, file system management, device management, security. Examples: Windows, Mac OS, Linux, etc. Compiler is a software that converts entire program code into machine language before execution, like C, C++. Generates an executable file for subsequent loading in main memory or RAM, so compiler requires more memory to execute. Faster execution as the entire program is in memory, though debugging is harder. Interpreter is a software that converts program code line by line in machine language during execution, like Python, JavaScript. No executable file generated, requires less memory for execution. Slower execution though debugging is easier. Please note that Java is both compiled and interpreted. First compiled to create bytecode and then interpreted to create machine language. An algorithm is a step-by-step procedure to solve a problem, for example, an average calculation for a few numbers or perform a task, for example, check whether a number is odd or even. It is used for logical problems, for example, calculating the maximum of two numbers, numerical problems, for example, an average calculation, and computational problems, for example, sorting a few numbers. Its key characteristics are: input. It should receive 0 or more well-defined data items, for example, a whole number for checking even or odd. Process. It should perform well-defined operations on the data, for example, clear steps of even/odd calculation. Output. It should produce a well-defined result, for example, even or odd. Definiteness. Each step should be unambiguous, for example, divide number by 2 or checking remainder for 0, etc. Finiteness. It should terminate after a finite number of steps, for example, ends after displaying odd or even. Generality. It should be general enough to apply a range of inputs, for example, any whole number can be checked whether even or odd. Let's now discuss the typical steps to solve problems using algorithms. 1. Understand the problem, identify requirements, inputs, outputs, and constraints. For example, input for odd-even problem is a number like 5, outputs, odd parity, and constraints, input should be a whole number. 2. Analyze the problem, break the problem into smaller and manageable parts. For example, we can break the even-odd problem into smaller steps. A. Input a whole number. B. Divide the number by 2. C. If there is no remainder, the number parity is even. Else the number parity is odd. 3. Design the algorithm. Devise a step-by-step procedure to solve the problem, for example, prepare a flowchart and pseudocode. 5. Implement the algorithm. Translate the pseudocode or flowchart into a program, for example, prepare a C code. 4. Test the algorithm. Verify correctness with sample inputs, for example, number 8 is even because it's divisible by 2. Number 9 is odd because it's not divisible by 2. Number 0 is even because it's divisible by 2. Number 8.5 is neither even nor odd because it's not a whole number. 5. Optimize. If necessary, improve efficiency in terms of performance and memory usage. For searching a number in a sorted list, repeatedly dividing the list in half will be faster than searching the whole list. Odd-even parity check problem is simple and already optimized, however, Time can be saved by hardware implementation in communications systems and memory controllers. Why do you need to represent an algorithm? It is needed to communicate ideas clearly and plan before coding. Methods of representation. 1. Flowchart is a visual representation using symbols. 2. Pseudocode is informal, text-based description of steps. Now, flowchart is a diagrammatic representation of an algorithm using symbols. Symbols used are start/end with oval symbol, process, rectangle, decision, diamond, input/output, parallelogram, and flow with arrows. Example 1. On a numerical problem, find the sum of two numbers. Consider the flow chart on the right to solve this problem. Pseudocode is a high-level, informal description of an algorithm using natural language and program-like syntax. It is easy to understand and modify, and there is no strict syntax rules. Pseudocode for number addition problem. Step 1, start. Step 2, input A, B. Step 3, compute sum equals A plus B. Step 4, display sum. Step 5, end. Number addition flowchart is on the right and already been discussed. Example 2, logical problem. Input a whole number and check whether it is even or odd. Flowchart shown on the right. Pause the video and check the diagram. Pseudocode. Step 1, start. Step 2, input n. Step 3, compute remainder equals n%2. Step 4, if remainder equals 0, display even. Step 5, else, display odd. Step 6, end. Comparison of flowchart and pseudocode. Consider visual appeal. Flowchart is graphical, easy to visualize, whereas pseudocode is text-based, less visual. Consider ease of use. Flowchart is complex for large algorithms. Pseudocode is easier for complex logic. Consider modification. Flowchart is harder to modify. Pseudocode is easier to modify. Consider audience. Flowchart is for non-technical users. Pseudocode is for programmers and developers. What is a program? It is an implementation of an algorithm using a programming language, e.g., even.c. Program also known as source code. Processed as follows. Algorithm source code compilation object code executable code, program. Program variables. Named memory locations to store data. Declaration, int n. Data types. Int, integer or whole number, for example, 10. Float, floating point number, for example, 3.14. Char, single character, for example, 8. Memory locations. Each variable is assigned a unique memory address. For example, consider the following line. Int n equals 7, n is stored at a memory address, for example, 0x1000. Int n equals 2, means. Create a box named n in the memory space and store number 2 inside it. N is in address 0x1000 means. The box n is stored at memory location 0x100000, like a house address. Think of it as n equals label, 2 equals content, 0x100000 equals address. Computer memory is a collection of many such boxes at consecutive addresses. Here's a recap of even-odd pseudocode. And here is its C program. You may pause the video and check the pseudocode steps with corresponding C lines of code. Program explanation. 1. Imports ready-made standard input-output functions, for example, scanf, printf in the C code with the use of #include. 2. Variable declaration, int n, means a box labeled as n is kept ready for storing numbers. 2. Input, scanf, %d, and n, inputs the number and stores in variable n in the main function. 3. Logic, calculates remainder using n modulo 2. If remainder equals 0, then the number is even else it is odd. 4. Output, prints even or odd. Compilation process. Source code compiler check for syntax errors. If yes, fix errors, or if no, create object and executable files. Compilation command on Ubuntu operating system is as follows. $gcc even.co even. Object code, intermediate code generated by the compiler, for example, .obj files in C. Executable code. Final output after linking object code with libraries, for example, even following the above compilation. Can be run directly by the operating system, for example, /even hashtag on Ubuntu operating system. Errors can appear during the program compilation and execution, syntax errors during compilation and logical errors during execution. Syntax errors. Violations of programming language rules. Detected during compilation. Example, missing semicolon, using int. Logical errors. Code runs but produces incorrect results. Not detected by the compiler. Example, using plus instead of % or swapping the displays in an even-odd check. Check the above diagram where multiple C and other language files are compiled and linked together to form a single executable file with single main function. It also mentions preprocessor and assembler. Preprocessor is a software tool that processes the source code before compilation. Directives start with hashtag and are executed before the code is compiled, e.g. File inclusion adds the content of a file to the source code, e.g. hashtag include macro expansion, replaces macros with their definitions, e.g. hashtag define pi 3.14159. Assembler, translate human-readable assembly language into machine code, binary, that computers understand. Learn more, history of computing. Numerical methods evolved in Babylon, China, and Egypt for land survey and tax collection, 3000 BC. Global adoption of abacus for fast computing. Invention of decimal number system in India, 800 AD. Invention of logarithm and Napier bones for multiplication by Napier, 1614. Devised slide rule by Edmund Gunter, 1620. Invention of Pascaline, first accounting machine, by Blaise Pascal, 1642. Design of analytical engine by Charles Babbage, 1834. Lady Ada Lovelace wrote the first computer program, an algorithm designed to instruct the analytical engine to calculate Bernoulli numbers. Devised Boolean logic by George Boole, 1854. First large-scale data processing made by U.S. Census Bureau, 1890. Dr. Herman Hollerith devised an electromechanical machine, tabulating data using punched cards. Dr. Hollerith started Tabulating Machine Company, 1896, later became a giant in the computing industry, known as IBM. Learn more, computer classification by generations. First generation computers evolved in 1940s to 1956. Technology used, vacuum tubes. Key characteristics, large size, high power consumption. Slow processing. Programming languages, machine language. Programmers had to write these binary code instructions manually and use punched cards or paper tape for the input. Imagine writing a long string of zeros and ones to perform even a simple task. Examples, ENIAC, 1945, UNIVAC, 1951. Second-generation computers evolved in 1950s to 1960s. Technology used, transistors. Key characteristics, smaller, faster, and more reliable, magnetic core memory. Programming languages, assembly-level language, Fortran, COBOL on batch operating systems with minimal features. Examples, IBM 1401, 1959, IBM 7094, 1962. Third-generation computers evolved in 1960s to 1970s. Technology used, integrated circuits. Key characteristics, smaller size, lower cost, modern operating system introduced. Programming languages, Fortran, COBOL, BASIC, ALGOL, Pascal, C on Unix or DOS operating systems. Examples, IBM 360, 1964, PDP-8, 1965. Fourth generation computers evolved around 1971 to ongoing. Technology used, microprocessor. Key characteristics, personal computers, PCs, GUI evolved, used networking and VLSI, very large-scale integration, general-purpose computing. Programming languages, C, C++, Java, Python, JavaScript on Windows, Mac OS, Linux. Examples, IBM PC, 1981, Apple Macintosh, 1984. Fifth generation computers evolved around 1985 to ongoing. Technology used, advanced processors like Intel Core and AMD Ryzen powered with graphics processing units, GPUs and tensor processing units, TPUs for advanced computing. Key characteristics, artificial intelligence covering machine learning, natural language processing, computer vision, robotics and expert systems, parallel processing. Programming languages, Python, R, Prolog, Lisp on Windows, Mac OS, Linux equipped with AI. Examples, IBM Watson, 2011, supercomputers like IBM Summit, 2018, cloud-based AI platforms like Google AI Platform, 2018, quantum computers, ongoing research in IBM, Google, etc. Typical hardware trend over generations, decreasing size and increasing performance. Learn more, computer classification, based on size. Supercomputers are the largest of all and most powerful, used for weather prediction, nuclear, aircraft/automotive design, online banking. Mainframe computers are also large and powerful, typical servers on World Wide Web, bank, airline etc. Connected with dumb terminals and intelligent terminals. Smaller and less powerful mini-computers, mid-range, used for small to medium-sized businesses for tasks such as accounting, inventory management, and database management. Microcomputer types, smallest but very useful for personal and professional uses, for example, desktop, laptop, workstation, network, and handheld devices like PDA, cellular phones and H/PC Pro devices. Learn more, binary numbering system. A base 2 numbering system using only 2 digits, 0 and 1. Each digit is called a bit, binary digit. Computers use binary because they operate using 2 states, 0 meaning off, no voltage, and 1 meaning on, voltage present. Binary to decimal conversion, each binary digit represents a power of 2, e.g., 1011 base 2 equals 1 times 2 to the power of 3 plus 0 times 2 to the power of 2 plus 1 times 2 to the power of 1 plus 1 times 2 to the power of 0 equals 11 base 10. Applications. Data representation, text, images, and videos are stored in binary. Computer processing, CPUs perform calculations using binary logic. Networking, data is transmitted as binary signals. A group of 8 bits is called a byte, which can represent 256 different values. 2. Computers use binary to perform all arithmetic operations, addition, subtraction, multiplication, division, e.g. addition, 1010 plus 1101 equals 10111, etc. Binary is the foundation of logic gates, and, or, not, etc., for logical operations using binary inputs. 0 and 1, e.g. 0 logical and 1 equals 0, 0 logical or 1 equals 1. Here are some short questions to test your understanding. You may pause the video and check these. If you're unsure of any answer, please refer to the unit materials and your textbook for clarification. Let's see if you've grasped the key concepts. Here are some descriptive questions to challenge your understanding. Feel free to pause the video and give them a try. If you need any help, don't hesitate to revisit the unit materials or your textbook. That wraps up Unit 1 on Computer Introduction. Get ready for the next unit, where we'll dive into the exciting world of C Basics. We'd love to hear your thoughts on these video sessions. Are they helpful? Is there anything you'd like to see more of? Please share your feedback, it helps us improve. Thanks for watching.